Okay, good morning, everybody. Welcome to another session of quantum mechanics. So we have been talking about angular momentum, and over the past several lectures, uh, we have gone over how one understands the spectrum of the angular momentum operators. So spectrum, I hope that you all understand. A spectrum basically means the eigenvalues. So what form the eigenvalues take, right? What their distribution is, that is the spectrum. And so what we have found is that, well, again, let me just the steps. Right. So first you construct a complete set of commuting operators. So in our case, that complete set becomes L square comma LZ, or L square comma LX, or L square comma LZ. It doesn't matter which one. And as I also explained last time, it can also be some linear combination of the three of these, right? So we normally, this is the default choice. Okay. So once we have this, then, so let's say that so this is called CSCO, complete set of commuting operators, complete set of commuting operators. Once you have the CSCO, then, so let us say that your complete set consists of some operators AI, where I goes from 1 to n. Okay. Then what does it mean to have a set of commuting operators? If operators commute, then they have simultaneous eigenvalues. So your states are labeled by eigenvalues of AI, of all the AI. So for instance, if you have a state, you would write it as with some labels, right? You would write it as with some labels. What would be those labels? Lambda 1, lambda 2, lambda n, where lambda I is an eigenvalue of the operator AI. Okay. Now you have actually seen an example of this. If you think about it, other than angular momentum, can you think of another example where you have a more than one operator and you have a set of commuting operators? Anybody?
Momentum or kinetic energy, sir?
Absolutely. Good. Momentum and kinetic energy.
Position or potential.
Is that if you are in more than one dimension, right? Then not just momentum and kinetic energy, you have Px, Py, and Pz, let's say, right? All of these commute with each other, right? And also the kinetic energy. So P square. P square is the sum of the square of all three. all of these commute with each other. So, right. So, for example, in the 2D infinite potential well, how do we write the states? We write the states as psi mn, right? Mn. What is m and what is n? These are the eigenvalues of the momentum in the x direction and the y direction, right? Okay. So, yeah, so we don't need all four of these operators. We need a complete set. So we can take either px, py, and pz, or py, pz, and p square, right? You can have different combinations. Let me actually make all this in blue only. So then after having constructed this complete set, right, then you try to find if there are any kind of ladder operators which take you between the different eigenvalues of the different of this set of operators. So ladder operators, right? So in the case of angular momentum, you have this L plus minus. If you take these operators, they will increase your LZ eigenvalue or decrease it. And if you look in momentum and position, right, then what are your ladder operators? You have A, right? A dagger and A. So instead of A dagger, one can call it A plus and A minus. And A plus minus is what it is. X plus minus IPX, right? So you will have one A for the X component, one A for the Y component, and the Z component. Then you ask, well, is there some algebraic constraint on the allowed eigenvalues? So if you look, for example, in momentum, right, there is no constraint. If I act with a ladder operator, your momentum states will keep increasing, right? M and N, there is no limit. But if you look in momentum, in angular momentum, right, there you have to use L square and LZ as a set of commuting operators. And then you have a limit on the maximum and minimum eigenvalues of LZ, right, which is set by the fact that L square minus LZ square expectation value is always greater than or equal to 0. Okay, so this is just to summarize the procedure of how you construct these states. So finally, for angular momentum, we are left with this, right? So for angular momentum, we are left with this labeling where L square has the eigenvalue j times j plus 1 and Lz has the eigenvalue m, right? So j is a measure of the total angular momentum and m is the component along the z axis. So in one direction, projection of the angular momentum in any one direction, and we have that the eigenvalues of j are going to take these, and m is m takes values in this set minus minus j plus 1 minus of absolute value of j plus 1 to j plus 1. No, sorry, not plus 1. What am I saying? So minus j plus 1 dot to j minus 1 to j. So how many such eigenvalues are there? If you count the number of m is 2j plus 1. Okay. Okay. Now let's see. All right. And here I should put a factor of h bar square and h bar to make the dimensions correct. Okay. I think so. Am I right? Let me just make sure. Yeah. Okay. So now you remember that if you have an operator, how do you characterize operators? You characterize operators by their matrix elements, right? So if you have some operator O and you have some set of basis states for your Hilbert space, phi I, then you say that this operator has matrix elements Oij, which are given by phi I O phi j. And if you know all the matrix elements, then that means you know the operator. Okay. Now, so, you know, at this point, I can continue talking about the matrix elements of j square and jz and j plus and minus, and we'll get some expressions. Okay. Now that will not necessarily tell us so much. So now at this point, I'm going to talk about this this rotation group, about the theory of the rotation group. So please ask me any questions if you have questions. Okay. So we will be doing we will look at this thing. Solved exercises, or I'll work out some problems in class I was suggested in the class committee meeting yesterday. So I'm trying to find some nice problems. Let me see. Okay, so no questions, huh? I mean, everybody very silent today. If you're so silent, then it kind of makes me also feel a little bit demotivated, I guess. Are there no questions, nothing? Maybe we'll just end this class here only. I think there's very little interest right now in learning anything. What do you say? Shall I call it a day and shall we start again tomorrow? You can be honest, huh?
No, sir, we are listening you carefully.
Nahi, you are listening, but there's like you're listening, but like it seems like you are in a comatose state, like so.
So I was just sharing my thoughts in your group, so that
Yeah,
I am listening to your lecture.
No, that's
But,
fine. That's fine. I'm
not-
not referring to anything that anybody said in the group or anything. I'm just like the general like sort of like environment, nah? Like even if it's not live, it's still an interactive class, and nobody is saying anything. There is no, so it is like okay. It seems that well maybe the maybe it's boring, and maybe you're not understanding, and or maybe sometimes the environment is just not that good now. So that's why I was asking, like, I mean, if you're not feeling it, then we can always come back tomorrow. Shall we try to do that? Nishita, see, normally Nishita at least is there and she says something, but even she is very quiet today. So I think today is just one of those days when everybody is out of focus. I'll continue tomorrow, okay? Because otherwise it doesn't help. I can keep talking and you can keep listening. But I think if there is today we are
sir,
missing
you can go on, sir.
Huh?
You can go on, sir.
On Sudeep.
Yes, sir.
Chalo, if Sudeep says I can go on, then I will go on. ठीक है. Okay. So now one thing is that if you like I've told you that I've been following Sakurai. So if you look at Sakurai, then for instance chapter 3 angular momentum is a very very big chapter. It's more than 100 pages, right? So there is too much material in it. Obviously we are not interested in covering all that material. Okay. So what are the important aspects that you should look at? One is this the what I've talked about, which is this group angular momentum operator algebra, and that actually starts in very late into the chapter, which is in section 3.5. So section 3.5 you should definitely understand. So now let me talk about this this rotation group, right? So what you have is, let me introduce the idea of a group. What is a group? How many of you know what a group is? If you know what a group is, can you raise your hand in the participants window? One person. Anybody else? Okay. So, all right. So, yeah. So let me talk about what a group is. Okay. So what group theory is looks at symmetries basically, symmetries of anything, symmetries of a system, which can be some kind of geometry, or it can even be some mathematical structure like a set or some other object. And so group theory looks at symmetries basically. So what are symmetries, right? What is a symmetry? So symmetry means that you take some system, right, and you apply some transformation to the system. And what happens is you get the system with some changes, right? It's the same system, but it appears in a different state. We should say it like that. So I put it system prime. The reason I'm referring to the system and not the state is because this transformation acts on all the states of the system, right? So if the system remains unchanged under the transformation, then we say that this transformation, we call it a symmetry. Okay, so an example of some of symmetries, for instance, is if you look at a square, let's say A, B, C, D. Okay. Now, if you take any permutation of the vertices, so if I take A, B, C, D, if I take any cyclic permutation to B, C, D, A or C, D, A, B, right? I will have the same object. It is just labeled differently, right? So we say that the square is invariant under these cyclic permutations of the vertices. It will be invariant under arbitrary permutations actually. So you can also have permutations such as BACD, where you switch to any two of the vertices like this. So this is one thing. Then let us put the this square in, let us put some coordinates. So let's call this X and let's call this Y. Okay. Now let's take a reflection across the Y-axis. Okay, so that means, what does it mean to take a reflection across the Y-axis? That means if you have a point over here with some coordinate X, Y, its reflection will have coordinates minus x comma y, right? So I put plus x here and minus x here because it doesn't matter, right? I mean, x can be a negative value, then minus x will be a positive value. So if I have two vectors like this, if I have a vector like this and a vector like this, let's call this v1 and let me call v2, then I would say that v2 is obtained by taking a reflection in the y-axis. Okay, so actually instead of r, I will use some other symbol. I'll use t of y, because r we will say for rotations. So t of y is your transformation. Okay. Right. Similarly, you can have a reflection along the x-axis. Okay. T of x. In general, right? In general, one can have a reflection along any line. So I will call that T of n hat. Right? N hat means the unit vector. So if you specify the unit vector, then you're specifying the line. So the reflection across that line, right? So now if you look at this square, right, you can see that if you reflect across the y-axis or if you reflect across the z-axis, the square will be left unchanged, right? You will just get some permutation of the indices. So if I reflect across the y-axis, what will happen? A and B, these two indices will get swapped. C and D, these two indices will get swapped, right? But I'll still have a square. So for a square, right? These are two symmetries: reflections along x and reflection along y, right? But I can have other symmetries also. Other than reflection along x and y, what other symmetries can I have of an object like this? Any suggestions? So I have two symmetries, Tx and Ty. Anything else?
Rotational symmetry.
Rotation by how much?
90 degree. Sorry,
R, right? And around which axis? So
X and
here
above.
I've not drawn the Z axis, right? So the Z axis would be coming out of the page. So we are rotating in the XY plane, right? So we are rotating around the Z axis. Or actually it is better to say RXY. That means we are performing rotations in the XY plane by pi by 2, right? So if you perform a rotation, so now I can let me write down the state of the square. Okay, so how do I represent the square? I can represent it like this. Like if I think of it as some quantum system, okay, I can write it as ABCD. This is my configuration. This is my state of the system, right? So what is the action of T of X on this ABCD? Anybody? Which indices will be exchanged? What will happen to the indices, vertices under Tx? You can just look at this picture and see what will happen, right? I'm reflecting across the x-axis. What happens?
BADC.
DC, yes.
Right. D, right. So under the reflection, what will happen is you're reflecting across the x-axis. So D and A will be switched. So you'll get D, and then B and C will be switched. So you'll get D, C, B, A. Right? Then if I
Yes,
take a
sir.
reflection along the y-axis, what will I get? Of A, B, C, D. I'll get B, A, C. Right? These two indices will be switched and these two indices will be switched. Now, what if I take two reflections across the x-axis? What will I get?
ABCD.
Yeah, sorry about that. My internet disconnected. Are you all there? Shubham?
Yes, sir.
Yes, sir.
So,
Yes, sir.
so if I take the square of this operator Tx, what do I get? If I take
ABCD.
two,
Sir,
huh?
same.
You get the same, right? You get A, B, C, D. So that means if I take Tx square, I get the identity. And if I take same thing for Ty square is also the identity, right? So I have right now how many transformations? Tx, Ty, and also the identity. Remember, the identity is also a transformation. It's a trivial transformation, but it's still there, right? What else? We have rotations by pi by 2. So if I rotate by pi by 2, what do I get? Others?
DABC.
Exactly. So what will happen? D will go to A will go to B, B will go to C, C will go to D. So you get D, A, B, C, right? And similarly, one can see that you can rotate by pi. If you rotate by pi, you'll get one more A, B, C, D. What will you get? You will get C, D, A, B, like this, right? Now, rotation by pi can be expressed as r pi by 2 square, right? That means if I take two rotations by pi by 2 and combine them, I get r pi. Okay. And then I have r 2 pi by 3, which is r pi by 2 cubed, right? And then finally I have r pi by 2 to the 4th power. What will this give me?
ABCD.
Identity, right? ABCD. So I have my set of symmetries now. It is r pi by 2. So I'll use a slightly simpler notation. I will refer to r pi by 2 as just r. Okay. So I have r square, r cubed. Right? So these are my group elements. I have these operations, all of these operations together, they form the group of symmetries. Now, why do I call them? Why do I call it? What is the, there is a certain structure that a group has. What is that structure? So a group is a set, right, with a multiplicative operation. Okay. So it has some operator which is called a multiplication. Okay. Such that, so if you take any two elements of the group, then you take the product of these two elements, that also gives you another element of the group. Okay. So for example, in this case, what is the product? The product is this repeated application, Tx, Ty, right? This is what I mean by product. And similarly, Ty, Tx is the product of Ty and Tx, right? So that means translation in, sorry, not translation, reflection along Y across Y and reflection across X. Okay. Now let me, let me see what happens if I take reflection across X and reflection across Y, Tx, Ty. What do I get? Tx, Ty, A, B, C, D. So first I have to act with Ty, which gives me B, A, D, C. Okay. Then I have Tx acting on this. Right. Now when Tx acts on this, what happens? I get the Tx operation acting on this will give me CDAB. Okay. Now, if you look at CDAB, can you relate CDAB to any of the other group elements?
R pi.
Which is equal to R square acting on ABCD. Right? So if I rotate by 180 degrees, I will switch the indices by two places, right? So A will go to C, B will go to D, and so on, A, B, C, D. So this tells me that Tx times Ty, if I multiply Tx by Ty, I get R square. R square is R pi by 2 squared. Okay. Now what about Ty times Tx? Can somebody work this out and tell me what the answer will be? So first you act with Tx, you get this expression. Then you act with Ty on this state, right? So what is the answer? Okay, if somebody can work it out quickly.
Same answer.
CDAB.
Identity.
R2.
CDAB.
CDAB.
So same, right? CDAB, which is also equal to R square. Okay. So in this way, I can look at all possible combinations of these group elements. So I can look at, what I can do is I can construct a group multiplication table, which looks like this. Like this. And then I can ask, for instance, what is identity multiplied by identity? Well, that is identity. So identity multiplied by anything will just give me the same thing, right? Okay. So let me put this in a different color. Let me call this green to distinguish it from. So these are your row labels and your column labels, and these are the results of multiplying the rows by the columns. Now, what about TX, TX? That gives me identity, right? What about TX, TY? TX, TY gives me R square. TY, TX gives me R square. TY, TY gives me identity, right? Then I can, then what is left? TX and R. So what is TX and R give me? Anybody? What will R do? It will shift everything by one index forward, right? It will rotate everything. And TX will then give me the inverse of that. So TX will give me C, what is it? 1 second. Let me just make sure I'm not making a mistake. A, B, C, D, D, C, B, A, right? This will give me C, B, A, D. Okay. Now what is C, B, A, D? C, B, A, D is, what is C, B, A, D? 1 second. So I will actually need to introduce some other group element. Okay. So this becomes complicated. That's why it's better to look at a different group. We can look at a different group, a simpler group. Let us consider just two elements. Okay. +1 and -1. Now, look at the product of these elements. What is the result? I get +1, -1, -1, and +1, right? So this is called the multiplication table. It is called the group multiplication table. Okay. And if AB is equal to BA for all AB belonging to G, then the group is called abelian. Otherwise, non-abelian. Okay. So an example of an abelian group. E to the I theta. Okay. Where theta goes from 0 to 2 pi. So basically the points on a circle, right? Now if you take this, we'll call this group U1. Okay. So if I take two elements of group 1 of U1, so I take e to the I alpha and e to the I beta, they are both elements of U1. So let's say this is e to the I alpha and this is e to the I beta. Now, if I multiply these two, what do I get? E to the I alpha, e to the I beta is equal to e to the I alpha plus beta, right? So e to the I alpha plus beta will give me, it will give me something like this. Right? The point is that this will give me another point on the circle. But what if I take e to the I beta, e to the I alpha? It will give me the same answer. Right? So this is an abelian group. U1 is abelian. Now, can anybody tell me what is the physical meaning of this group? Jatin? What does this group represent physically? Manoj?
Reflection along diameter.
Huh? Sorry? I missed what you said.
Reflection along diameter of circle.
Selection,
Reflection.
reflection. No,
Along
not
the-
reflection. No, not reflection. There's no, not reflection. Just think of it physically. What is going on here? You have a disk. You are just rotating the disk, right? What is it? So, anybody else? Aditi? What is this group? So let me give you something like this. Okay, I have an object like this. I have an object like this. Okay. If I apply this group e to the I alpha to this object, what will be the resulting object? Let me apply e to the I pi by 2. What will be the resulting object?
Rotated.
Yeah, I will get this, right? Yes.
Yes, sir.
So then what are these operations doing? What is e to the I alpha doing?
Rotate.
Sir, I think phase changes the phase. Physically meaning.
Changes the phase, but in a physical sense, in a very physical sense, like something you can do with your hands. What is it doing?
Rotation, sir.
Displacement.
Rotation by an angle alpha, right? So you can call it is a kind of a displacement, but it's an angular displacement, right? Not a linear displacement. So this group U1, this is the group of rotations in how many dimensions? Is this in 3 dimensions? Varun?
2 dimension.
2-dimensional.
In 2 dimensions, right? It is a group of rotations in 2 dimensions, right? Now, is there any other way to express rotations in 2 dimensions? So let's say I start with a vector, a two-dimensional vector xy. Okay. And I perform a rotation along around in the plane by an angle theta. Then how do I relate x prime y prime to xy?
Rotation matrix.
Everybody knows this. You have all studied this many times, right? Right. So I will call this r theta. Right. And it's a matrix, right? Now, if I take two rotations, one rotation by theta and another rotation by theta prime, and I multiply both of these together, what do I get? What is the result of this?
Rotation by theta plus theta prime.
Rotation by theta plus theta prime. What about r theta prime, r theta?
Same, sir. They will commute.
It commutes, right? So this is an abelian group. How many parameters am I using to label this group? So the group elements, to label the group elements, how many parameters am I using?
The angle of rotation only.
So one parameter.
The angle
Right?
of rotation.
Right. So this is also equal to U1. This group, which is represented by matrices, is the same as the group which is represented by these phases. Right? So these are, we refer to these as representations. So if I have a group element r theta, okay, I can write it in two ways. I can write it as a matrix, or I can write it as a complex number, I to the I theta, right? These are two different representations. I call this a one-dimensional representation, and this is a two-dimensional representation. Okay. So you see that a group is an abstract object. So the group elements, when I say that the group has some element, the element is not e to the I theta or this rotation matrix. The element is some r theta, it is some abstract object. When I ask what is the group acting on, right? What is the group acting on, right? So for instance, if I say on 2D vectors, right? Then what is the correct representation? The matrix representation. But what if it's acting on something else? For instance, in electromagnetism, right, electromagnetism, if you have a charged particle, so on a charged particle, what happens? You can take the state of a charged particle and multiply it by a phase, right? So in this case, what is r theta? R theta is represented by e to the I theta. Right? This is not as physically intuitive as this one, but they are both group representations. Here it is acting on a two-dimensional vector space, and here it just acts on some state psi. Okay. So another property of the group is that for all elements A in the group, there exists an element which I call the inverse of A, such that if you take the product of A and A inverse, you get the identity. Then there exists a special element called the identity, such that for all A belonging to G, A times the identity is equal to A is equal to identity times A. Actually, this one should go first. And then for all AB, this is the first, these are the group axioms. There exists C belonging to G such that C is equal to AB. These are the group axioms, 1, 2, and 3. The first one says that the group is closed under the multiplication. So this I will call closure under multiplication. This second one is called the existence of identity. Element means that there is one element which plays the role of the number 1 basically, and this is called existence of the inverse. Okay, so all of this actually should be covered in your mathematical physics course, but again, I don't know, for lack of time, maybe sir might have skipped this. Okay, but group theory is a very, very important part of physics. So if you don't know group theory, then you're like one complete whole section of physics you will never be able to understand. So you have to understand group theory. Okay, you can't, there is no shortcut around it. You don't have to understand group theory in every detail. Okay, just like you don't have to understand, so you need to know linear algebra, right, to study physics, but you don't need to know all of linear algebra. Linear algebra is a vast subject, right? You only need to know enough linear algebra to be able to do whatever physics problems. Same way, you need to know the minimal amount of group theory you need, okay, to apply it to physics problems. So I'll talk more about this in our next class tomorrow, okay? And right now I'll stop because I guess we have had a long enough class. So let's see, any questions? No questions in YouTube. All right, let me stop the recording. Actually, can you guys ask any questions while the recording is going on? That way other people can also learn from your doubts.
Actually, sir, I had a doubt regarding the question you gave in homework, a question in that.
Homework, okay, homework doubt. Yeah, that is important. Tell me.
Yes, sir, there was a question that we need to find the P by dt, like expect the rate of change of expectation value of P with respect to time.
Right.
And for ket n and ket alpha.
Right.
Yes, sir. So, sir, like, may I show you the solution or something? Like, is
Yeah,
it
yeah, please.
visible, sir?
1 second. Let me. So dp by d alpha. Go up a little bit. Yes. Right. So you write P as this. Okay. Then next, go down, go up, and then go up. Okay. Then what about the time derivative? How
Time
do you get the
derivative will
time?
be 0 because these are all fixed values.
Right.
Right, sir. So,
So
but
right. So okay. No. 1 second. So dp by dt for let me actually just really quickly go and refer to the textbook because I don't want to say anything incorrect.
Sir, I think it will be 0 because momentum commute with Hamiltonian.
Who is that? Vipul?
Yes, sir.
Yeah, actually, Vipul, you're right.
No
Well,
need.
but you have to be a little bit careful, okay? This is expectation value, right? But yeah, dp by dt is
Yes, sir.
going to be equal to IH bar H
Yes,
comma
sir. I
P.
already derived the formula, no, sir.
So you're right. So the expectation value will be 0. Right. Good. Now, 1 second. Right. Yeah. It'll be 0. What about dx by dt?
Sir, it will be not 0. I calculate.
it will be I by H cut,
Yes.
commutator of Hamiltonian and X at T naught. Sir, you are muted.
I got disconnected. Yeah. Tell me.
Yes, sir. It will be equal to I by H cut and commutator of H Hamiltonian and X at T naught.
Right. So will it be 0?
Like if X by T naught, X at T naught is a constant, that then the commutator will be 0, and then it will be
Right.
0.
No.
No, sir. I think no.
No. This will not be 0. Okay. If you take the commutator of H, and also one thing. What was that statement just now? Somebody made that commutator of H with P is 0.
No, sir. I said that.
No, not you, Shantanu. Before that, somebody else
Yes, sir.
like this, no?
E.
Vipul,
Yes, sir. Yeah.
what is the Hamiltonian?
Hamiltonian is minus h cut square by 2m d square by del square
It
by
is p
d.
square plus x square, no?
Yes, sir.
I mean, except for some constants.
Yes, sir.
So if you take the Hamiltonian and take the commutator with the with momentum, what do you
Yes, sir.
get? Do you get 0?
Yeah. Yes, sir. I,
No, sir.
Really?
We will get
sir,
minus dv by
if
dx.
you take
You get
commutation,
x.
you got a triple
You get
derivative.
x.
Yes.
Commutator of p square with p is 0, right?
Yes, sir.
But you have an x square part also, no? So is the commutator of x square with p 0? What is this? X comma p, right? Which is not 0, right? So this will not be 0. Okay.
Sir.
Yeah.
So the commutator of H and P came out to be the gradient of the potential V.
The commutator of x and p comes out to be the gradient of the
H and P.
potential.
He's telling about the Ehrenfest theorem. He's using that.
The commutator of p and vx, sir. Commutator, if general.
Commutator
Sorry.
of, right, commutator of p and vx, right?
Yes, sir.
Not commutator of. So this is true for any function, right? That if you take commutator of p and any function of of x, right? This is another problem that I've given you, right, in the homework.
Yes, sir.
Then what is this? This is equal to minus IH bar df by dx, right? And similarly, if you take commutator of x with any function of p, what do you get? You get IH bar df by dp. And I think you'll probably need to put an h bar in the bottom over here, I by h bar. So how do you huh?
Sir, your screen is not visible, sir. Writing is.
I can see the update happening. Anybody else having any problem with this?
No, sir.
No, sir.
Vipul, can you? I'll just 1 second. I'll just restart my screen sharing. Okay, 1 second. Tell me if that fixes it. Is this better?
Yes, sir.
Okay. So okay. So to come back to the original question, is this 0? No, this is not 0. Okay, this is given by this expression. This expression is not 0.
Sir, but
Okay.
commutator of H and P, and we
commutator of 1 second. Commutator of
H and P.
x and p. Okay.
H Hamiltonian.
Hamiltonian with p. Okay.
Hamiltonian has a p square term and an x square term.
X square term. That's right.
And the p square term goes.
P square term goes.
And what will left with only the x square term.
X square term, right?
And x square term, it's actually the potential term, right?
That's the potential. That's right.
So the like you wrote in the next page,
Right.
the x and vx, the p
Right.
and vx,
Right.
and p and vx is IH bar dou v by dou x, right?
Right.
and the expectation
So
value.
that's exactly the answer I'm getting now. With a minus sign, I should probably put a minus sign over here.
But sir,
Right? If I take p and x square, what am I getting? I'm getting minus ih bar. What is d of x square by dx? It's 2x, no?
and we have to take the expectation value of that, right?
So if f of x is equal to x square, then df by dx is 2x, right? So p comma x square is equal to minus 2ih bar x.
And we have to take the expectation value of that, right?
Right.
And the expectation value of x when the state is n is 0.
Okay.
But then that equation is 0, right?
But is it 0 in alpha? Is the expectation value of x 0 when you are in this coherent state? This is a coherent state, right?
If the eigenvalue of that alpha doesn't change with respect to time.
So how do I write x? X is equal to a plus a dagger by 2, right?
Yes, sir.
So what is the expectation value of x in this state, alpha?
Alpha star plus alpha.
Right. Is that 0?
But the rate of change of alpha star.
No, no, 1 second. So it is equal to Re alpha, no?
Yes, sir.
Right. Okay. And the same way, if you look at the expectation value of P, what will you get? You will get imaginary value of alpha, right? So
Yes.
this actually tells you what the physical interpretation of this alpha is, first of all. It tells you that if you look at the phase space and you pick any point in the phase space, right? That point in the phase space, you can think of that as alpha. It has coordinates x comma p, where you think of this as the imaginary axis. But yeah, this is not 0, no? So this will also not be 0. Expectation value of dp by dt will not be 0. And this makes sense because if you remember, for a harmonic oscillator, okay, what is the
But sir, expectation value of momentum in harmonic oscillator is 0, na sir?
Why is it 0? It depends on the state. It depends on the state in which you take the expectation value, right? If your state is an energy eigenstate, then it's 0. But if your state is a coherent state, is a coherent state an eigenstate of energy? Is it an eigenstate of the Hamiltonian of the number operator a dagger a?
No, sir.
Yes,
alpha
sir.
Is no, it's alpha is an eigenstate of a. Right? But it's not an eigenstate of the Hamiltonian. And what is the Hamiltonian? H bar omega into a dagger a plus 1/2. So it's not an eigenstate of a dagger, right? This is proportional, so not alpha. It's like not proportional to. Okay. So there is no reason for this to be 0. And now remember for the harmonic oscillator that if you look at the solution of the harmonic oscillator, what do you get? You get something like this. X of t is equal to some a cosine omega t, let's say. Then from this, if you calculate the momentum, what is that? M dx by dt, right? What do you get? Minus a omega sine omega t, right? Now, if I take dp by dt, what do you get? You get minus a omega square cosine omega t, right? I can write this as minus omega square x of t. Right? So this makes sense that what am I getting? I'm getting, if I take the expectation value of dp by dt in the coherent state, right? I'm getting something which is proportional to x, or more precisely proportional to the expectation value of x. So this is the reason why we refer to the coherent state as a classical state, because it obeys these classical equations of motion. Is this any clearer? I don't know. I mean,
Yes, sir.
do you want me to go through the calculation again?
No, sir, it's fine.
Okay.
Fine,
Okay.
sir.
Any other question? Next question. So all of this comes under homework revision. Next question. Okay. So anybody else who wants to ask anything else? If you don't want to ask, if you don't have any doubts, then you can go. I mean, I'm not holding anybody here. If you have a doubt, you can stay and you can ask. And if you want to listen to the answers, you can also stay. Okay, I'll stop the recording.